Hello and welcome to the second lecture in Module 2. I am Dr. Jason Mast, and in this lecture we will cover forces and momentum. That concludes the part of our lesson on motion, where we described and quantified motion. However, we did not discuss the cause of motion, and that is the topic of the next section. Forces are the cause of motion, and Newton's second law tells us the relationship between force and acceleration. Forces. These push or pull an object in a certain direction with a certain amount of strength. The SI unit of force is the Newton, or capital N for short. This is Newton's second law. The net sum of all forces acting on a piece of mass is equal to the product of the object's mass and its acceleration, and is written as the net force equals ma. Mass quantifies an object's resistance to change in its motion. For example, a very massive boulder is more difficult to move than a soccer ball. Force is the source of acceleration. Here is an object of mass m, and three forces are acting on it. You can see from the arrows in which direction the force is pushing or pulling it. We need to find the net force, and this is found by taking the vector sum of those three forces, and this is what that looks like. We have found the net force by adding the three force vectors, and we got this vector. To find the acceleration, we take that vector and divide by the mass. Because the mass is positive, the acceleration will be in the same direction. We have now found that the object will accelerate in that direction, and the amount of acceleration can be found by taking the net force and dividing by the mass. Let's do an example problem of accelerated displacement. A 3.1 kilogram object is accelerated from rest by a 6.6 Newton force up to a speed of 2.9 meters per second. What is the object's displacement? Here's an image of the object that is 3.1 kilograms with a 6.6 Newton force acting on it. Step 1 is to draw an image and label what is known and what is asked for in the problem statement. So we know that it starts from initial velocity of 0, has a displacement of delta x. Once it gets up to that displacement, it has a final velocity of 2.9 meters per second. Now we need to pick a coordinate system. This is a 1D problem. We will take motion on the x-axis and take x equals 0 and t equals 0 when the object starts moving, and it will move in the positive direction. Now we need to identify the relevant equations. For this problem, Newton's second law, F equals ma, will be relevant, and the last kinematic equation, v sub f squared equals v sub I squared plus 2a delta x. Then we will use those equations to solve for the acceleration and then the displacement. We can get the acceleration from Newton's second law by taking the force and dividing by the mass. In the end, we get 2.1 meters per second squared. We can then plug that into the kinematic equation and solve for the displacement. Here I have highlighted the velocities in green and the acceleration in red to help guide you. You should notice that I include the units in my work. In the end, when everything is done, we get 2 meters of displacement. Let's now look at a few different types of forces. First are weight and the normal force. Objects that are near the surface of the Earth are pulled downward. The rate of pull is 9.81 meters per second squared, and you should memorize that value. The force associated with this pull is called weight, and it is equal to the mass of the object multiplied by the acceleration due to gravity, and this force vector is always downward. An object resting on top of another object cannot pass through it. The force responsible for this is called the normal force. The normal force is perpendicular to the surface. Here is a table with a block on top of it. Because that block is on the surface of the earth, it has weight, and the weight points straight downward. However, that block cannot pass through the table. The table is providing a force pushing it upward. That force is called the normal force, and is given the symbol N. Because this object is at equilibrium, meaning it is not accelerated, the normal force and the weight are equal. Here it is important to note, weight is always straight downward, and normal force is always perpendicular to the surface. Let's now discuss Newton's third law of motion. Newton's third law says that for every force there is an equal and opposite reaction force. For example, if a hammer strikes a nail, the hammer acts on the nail with an impact force to drive the nail into a piece of wood. But the nail also impacts an equal force onto the hammer. A common task is for students to identify action-reaction pairs. In the case of a hammer and a nail, it is fairly obvious what the action-reaction pair are. The action is the force of the hammer onto the nail, and the reaction force is the nail's head onto the hammer. However, it is not always obvious. For example, the normal force and weight on the previous slide are not an action-reaction force pair. Here is one action-reaction force pair. The block is on a table. Because it cannot pass through it, the table provides a normal force to keep it on top. However, the block is also pushing downward on the table. That is a reaction force. It is also a type of normal force, but is going in the opposite direction. And we just give it the symbol N prime. The other pair is the pair of weights. Because the block is on the earth pulls it downward with a weight force. But there is a reaction force, and that is the block is pulling the earth upward with the same amount of force. Let's now look at tension as a force and Atwood's machine as an example problem. Tension is a pulling force through a cable or a rope, and it is always a pulling force. It never pushes. The magnitude of tension is the same everywhere in a rope. Here is a blue object that is pulled through a rope. Because the object is on the earth, it also has weight, mg. If we take up to be positive, the equation of motion for this object is tension minus the weight is the object's mass times its acceleration. Let's now use this to analyze Atwood's machine. An Atwood's machine is a machine composed of two unequal masses that are connected through a rope over a massless pulley that is free to rotate. The task is to find the acceleration of this system. In this problem, I will take mass 1 to be the heavier object, and I will draw it as a larger object as well. The first step is to pick a direction of motion. And for these kinds of problems, it is usually easier to take the direction of motion for each object to be positive. For mass 1, because it is heavier, it will move downward, and so for it, we will take downward as being the positive direction. Because mass 2 is pulled upward, for it we will take the upward as being the positive direction. The next task is to draw the free body diagrams for each object. This is a process of identifying each force on each body in the problem. And this is what that looks like. Each mass is on the earth and so therefore has weight. Mass 1 is heavier than mass 2 and so its weight vector is longer. The two objects are connected to each other through a rope. The tension in the rope must be the same at both ends and everywhere along the rope. And so therefore the length of the tension vector is the same for both mass 1 and mass 2. Additionally, tension always pulls. And so for both objects, the tension is upward. Next, we will write down Newton's second law of motion for each piece of mass. Here is Newton's second law for the first object. It is the weight minus the tension equals its mass times its acceleration. You can see that because we took down to be positive, we add the weight. tension is in the opposite direction, so therefore we subtract the tension. We will do something similar for mass 2. Because up is positive, the order of subtraction is backwards. So for mass 2, Newton's second law is tension minus its weight equals its mass times the acceleration. Because these two objects are connected to each other through a rope, the acceleration of both objects will be the same. And because they are both accelerating in the direction of motion, it'll be the same sign as well. The final task is to solve for the acceleration. This is easily done if we take those two equations and add them together. You can see that on the left-hand side we will get a difference of weights and the tensions will cancel. On the right-hand side, the masses will combine. Then we can solve for the acceleration, and we get that the acceleration is equal to the difference in masses divided by the total mass, then multiplied by the acceleration due to gravity. Let's now do an example problem of finding the tension in a tethered ball's rope. A 2.3 kilogram ball is swung in a horizontal circular orbit with a 2.4 meter diameter circle and at a constant speed of 1.8 meters per second. How much tension is in the rope? In the animation below, all of the vectors are drawn. The green vector is the velocity vector of the object. You can see that its length never changes. That is because it is moving at a constant speed and undergoing uniform circular motion. The acceleration, shown in red, is centripetal and it is center-seeking. The only force acting on this is the force of tension in the rope holding the ball in its circular orbit, and that will be in the same direction as the acceleration. To find the tension, we need to find the acceleration and multiply it by the object's mass. We know that the mass is 2.3 kilograms, the speed is 1.8 meters per second, the diameter is 2.4 meters, and so therefore the radius is 1.2 meters. The tension will be equal to the object's mass multiplied by its acceleration. The acceleration is the speed squared divided by the radius. All that's left now is to perform the computation, which looks like this. And in the end, we get that there is 6.2 newtons of tension in the rope. Imagine a large body of fluid such as water. Then select a volume of that liquid. That volume of liquid has a weight that is equal to its mass multiplied by the acceleration due to gravity. The mass of that volume can be found by multiplying the density of the liquid and the volume that it occupies. This volume of liquid is at equilibrium and is just sitting in place, and so its acceleration is 0. Because the volume is at equilibrium, there must exist another force that balances the volume's weight. That force is called buoyancy. Any object that is submerged in a liquid will be pushed upward by the buoyant force, and its magnitude is equal to the liquid's weight that would have been in that object's location. It is equal to the density of liquid multiplied by the volume multiplied by the acceleration due to gravity. Drag and friction are forces that are opposite an object's motion and bring it to a stop. Because of that, they are classified as retarding forces. Drag is a force between the surface of an object and the surrounding fluid. The fluid may be air, water, oil, or something else. The drag force is proportional to a power of the object's speed. For small and slow-moving objects, the power is 1. For fast-moving objects, the power is 2. You should note that faster-moving objects will have more drag, slowing them down even more quickly. The proportionality constant depends on the fluid's density and the object's geometry. More dense fluids generate more drag, and smooth surfaces will have less drag. Additionally, smaller cross-sectional surfaces will have less drag. When an object is falling through a fluid, there will be a point where the object's weight and the drag force balance. Because the net force is 0, the acceleration is also 0, and the speed is a constant called the terminal speed. Friction is a retarding force between two surfaces. There are two types of friction, kinetic friction and static friction. Kinetic friction is the friction between surfaces in motion. For example, an object that is dragged along the floor will have kinetic friction with the floor. The direction of kinetic friction vector is opposite the velocity vector of the object. A simple model of friction is that its magnitude is proportional to the normal force. The proportionality constant is called the coefficient of kinetic friction and varies between 0 and 1. Static friction is friction that will prevent an object at rest from undergoing motion. Its direction is opposite the direction of the tendency of motion, and its magnitude varies to match the force that is attempting to cause motion, but there is a maximum amount of static friction called the coefficient of static friction. For example, if a heavy crate is pushed, there will be static friction that is opposite the pushing force. But once the pushing force is large enough to move the object, there will be kinetic friction between the bottom of the crate and the floor. Furthermore, the force needed to keep the crate moving will be less than the force needed to get the crate into motion. The coefficients of friction depend on the materials involved. Isaac Newton developed a law of gravity to explain the motion of satellites and planets in our solar system. He found that the gravitational force between two massive objects has these properties. It is proportional to each object's mass. It is inversely proportional to the square of the distance between the two objects, and because of this, it is referred to as an inverse square law, and it points in the direction toward the other object. Putting that together, we can get this equation, where the force of gravity equals a proportionality constant, g, times the mass of the first object times the mass of the second object, divided by the square of the distance between them. Where capital G is a proportionality constant, it is called Newton's gravitational constant, and it has this approximate value. In this image, there are two massive bodies. Each of them attract each other through a force of gravity. The magnitude of this force is the same for both objects. The distance between these two objects is r, and the force points directly towards the other object. The final topic is momentum and Newton's first law of motion. You probably noticed that we skipped Newton's first law and we started at Newton's second law. And the reason for that is because we need to develop an understanding of momentum, which we get from Newton's second law, to better understand Newton's first law of motion. So let's go ahead and do that now. So we'll start by writing Newton's second law of motion, F equals ma. We will then take this equation and replace A with its definition, A equals delta V over delta T. And then because the mass is constant over that time interval, we can put the mass inside of the numerator's delta symbol. And we get that F equals delta mv divided by delta T. We will then give the product mv a new symbol, P, and we call that momentum. We get that F equals delta P over delta T. Momentum is what Isaac Newton calls the quantity of motion, and it is defined as mass times velocity. If it is the case that the net force acting on a particle is equal to 0, then it will therefore also be the case that its change in momentum is also 0. And so therefore the final momentum will be equal to the initial momentum. This is called the conservation of momentum. Momentum is conserved, meaning it doesn't change, when the net force acting on a system is 0. This is Newton's first law of motion. An object at rest will remain at rest unless acted on by a force, and an object in motion will continue with that motion in a straight line path unless acted on by a force. you can see that Newton's first law of motion resembles the law of conservation of momentum. Momentum doesn't change unless there's a force acting on it, and if it has motion, that momentum will remain constant. We can now take Newton's second law and rewrite it. We'll take it and multiply both sides by delta t, and we get a new quantity called impulse, and that gives us the impulse momentum theorem. Impulse, which is force times the time interval, is equal to the change in momentum. Let's now do some example problems involving conservation of momentum and impulse. A 3.2 kilogram toy car moves on a frictionless surface at 1.8 meters per second. At one point, a part of the toy with a mass of 0.5 kilograms falls off. What is the speed of the toy car after the part falls off? The net force acting on the car is 0, and so therefore momentum is conserved. Momentum after the part breaks off can be written as the new mass, which is the original mass minus the mass of the part that breaks off, multiplied by the new speed. The initial momentum can be written as the original mass multiplied by its original speed. We can take that equation and solve for the speed after the part breaks off, and then plug in the values. After performing the arithmetic, we get that the speed after the part breaks off is 2.1 meters per second. You can see that the speed had to increase when the mass decreased in order to conserve momentum. A 3.2 kilogram toy car bounces off of a wall after a head-on collision while traveling at 1.8 meters per second. What is the impulse? Then, if the collision takes 2.5 milliseconds, what is the average impact force with the wall? We can start with the initial momentum, which is just the mass of the car multiplied by its speed. And we can draw the velocity vector like this. Here, we will take motion to the right to be positive. A head-on collision will cause the car to bounce backwards, and so its speed after the collision will be the same, except its velocity will be in the exact opposite direction. We can draw its velocity vector like this, and so the momentum after the collision with the wall can be written as negative mv. The impulse, which is equal to the change in momentum, will therefore be negative 2 mv, and its velocity vector will look like this. Putting in the values, we get that the impulse is negative 11.5 Newton seconds. The negative sign just means that it is opposite the direction of the original motion. The impulse momentum theorem tells us that the impulse is equal to the average force multiplied by the time interval. We can then solve for the force by dividing by the time, and then converting milliseconds to seconds and newtons to kilonewtons, we get this expression. After performing the arithmetic, we get that the average force is 4.6 kilonewtons, which is approximately 1,000 pounds of force. The negative sign only indicates that the direction is opposite the original motion. Here, this force would be opposite the direction of the original motion. That's what causes it to change direction. Let's now do an example problem of computing the impulse on a ball bouncing off of a wall. A 0.43 kilogram ball is bounced off of a wall. The ball hits the wall at 1.13 meters per second and bounces back at 0.91 meters per second. What is the absolute value of the impulse on the ball? The first step is to pick which direction is positive. And for this example problem, we will take the initial motion to be in the positive direction. Next, we will compute the momentum of the ball before the collision. Momentum is mass times velocity, so we take the mass of the ball and multiply by the initial velocity, and we get 0.43 kilograms times 1.13 meters per second, and we get 0.49 kilogram meters per second. This green arrow represents the initial momentum of the ball before it hits the wall. Next, we will compute the momentum of the ball after it bounces off the wall. It is computed similar to the initial momentum, except that the velocity is different. In this case, the value is different. It is now 0.91, and it is negative because it is bouncing back, so its velocity is in the opposite direction. So we get that the momentum after the collision is 0.43 kilograms times negative 0.91 meters per second, and we get negative 0.39 kilogram meters per second. This green arrow represents the momentum vector after the collision. You can see that it is shorter because the amount of momentum is less, and it is pointing in the opposite direction. The final step is to subtract these two values and take the absolute value to get the impulse. The reason we are taking the absolute value is because the problem statement tells us to do so. So the absolute value of the impulse is the absolute value of the final momentum minus the initial momentum. And when that is done, we get positive 0.88 kilogram meters per second. This green arrow represents the impulse vector. And you can see that it is the result of subtracting the final and initial momentum vectors. That concludes the lesson on forces and momentum. First, we looked at the various types of forces and Newton's laws of motion. You should review these and be able to describe and quantify each force, and then identify the direction in which the force causes changes in motion. Then we looked at momentum as a quantity of motion, and saw that it is conserved when the net force is zero. Additionally, we looked at the impulse momentum theorem, which relates force and changes in momentum.